Unit 4, Electricity and Magnetism, and we're on Concept 2, and we're going to be talking about electric current. And this is what really interests me about all this, because if you're in my class, you know I love the math, and I just think it's so interesting, and if you're anything like me, you've missed the math. We haven't done math in like an entire concept, so you're going to get your math fixed today. But this is where it really interests me, and also I just think this picture is stunning, but I want to talk to you about current. So electric current, which we abbreviate with a capital I in mathematical equations, it's the net movement of electric charge in a single direction. And this is what you have flowing through the wires into your house, powering all of the things. It's measured in a unit called amperes, which is abbreviated as amps. And here's what I find so fascinating. Electrons move in kind of a funny way. I like to say, imagine if you had a giant box of bouncy balls and you threw them down the staircase at your school. That is how electrons move. They're not holding hands like in kindergarten class, walking single file in a single direction. Yes, they are moving in a single direction, but they're moving crazily. And here's what's kind of interesting too about this unit amperes, just to give you some perspective. 1 ampere is 6.24 times 10 to the 18th electrons flowing past a given point every second. Okay, so that means, just to give you context for that number, all right, that's 6,240 million billion electrons flowing past a given point every second. That would be writing down 6,240 and then adding 15 zeros to the end. That's how many electrons we're talking about in just 1 ampere. So kind of crazy, and just, I think that's so interesting. So how do we get this current to flow? Two main things play into it. One of those being voltage difference. The voltage difference, which is abbreviated as a capital V, is the push. It's the force that's causing charges to move. We measure it in volts, which is abbreviated as a capital V, and charge flows from areas of high voltage to areas of low voltage. So what we do is anywhere where there's current flowing, I like to think of it as a slide. We create these differences in voltage, this higher voltage area and the lower voltage, and that allows the current to go down the slide, to go from high to low, and it pushes it. Think too, the larger the difference, the greater the current. The steeper the slide, the bigger the difference in the high to low, the faster that charge or that current can flow. So in this picture, if I have a bunch of charge on this end, lower voltage here, that's going to really push those charges in this direction. If that difference was greater, it would push the charges even more. Now, talking about that current, in order for current to flow, it needs to have a circuit. It needs to have a closed path to travel through. So looking at these two pictures, notice the difference. Okay, in this picture, the switch is open. That is not a closed path. This is an open path. Thus, you'll notice the bulb is not lit. Whereas in this picture, that switch is closed. Thus, the current is able to flow and the light bulb is able to be lit. This is necessary in order for electric charge to be able to move. If the switch is open, the current will not flow. If the switch is closed, it will flow. Now, I told you this was a switch, and you probably recognize this as a light bulb, but what is this thing? Anyone know what those are? Because that's pretty key to a circuit. That is your battery. So a battery is a device. It's going to convert chemical energy to electrical energy. So hopefully you remember learning about energy conversions or energy transformations when we learned about the law of conservation of energy in our last unit. So we're taking chemical energy and we're using that to create electrical. How they work. Basically, chemical reactions are happening inside the battery. And these reactions create that voltage difference between the positive and negative terminals of the battery. Because we have that voltage difference, if those terminals get connected in a circuit, then electric current can get pushed through the wire or pushed through the conductor material. Because of this voltage difference, again, that voltage difference is what pushes, it allows that charge to move. E are going to flow from the negative end, because that's the end with the higher voltage, towards the positive end, which has the lower voltage. So that's what's going on in those batteries that are, making all of the things that you use work. Your calculator, your phone, whatever it is that has a battery, that's how it's working, which is pretty cool. Now, current doesn't always just flow easily. There is something that kind of prevents the flow of current, and that is called resistance. Resistance in an equation is a big R, and it is the tendency of a material to oppose the flow of electrons through it. We measured in ohms, which is the Greek omega sign for the unit, which is kind of fun to draw. And so it's affected by four things. So first is the material. Insulators have much more resistance than conductors. So obviously insulators are going to prevent the flow of current. Conductors are going to encourage the flow of current, if you will. Also the size of the wire. Think about the diameter. I told you that electrons move like a bunch of bouncy balls thrown down a staircase. If you have a really, really narrow wire, then those crazy electrons are going to be bouncing off each other like crazy and not able to flow easily. So that's going to create more resistance than if there was a larger diameter that could allow those crazy bouncy balls of electrons to move through. Also the length of the wire. The longer the wire, the more resistance. There's a longer pathway for that current to travel through. Thus, the length of it is just going to create more resistance than a shorter wire, which would have less resistance and allow the current to flow a little easier. And last is temperature of a wire. So hopefully you remember from our last unit that temperature is a measure of the average kinetic energy of particles in an object. So higher temperature means higher kinetic energy of particles in the object. And hopefully you remember that kinetic energy is energy in motion. So if higher temperature means higher kinetic energy, that means the particles are moving crazier. So the electrons are going to have a harder time flowing because they're bouncing even crazier than they were before. So a higher temperature of a wire is going to also have more resistance. So how do we put all this together? Current and voltage and resistance, the three things that kind of work together on this. And we put it together with Ohm's law, which says that the amount of current is directly proportional to the voltage difference. So what that means in simpler terms, the higher the voltage, think the greater that slide, the steeper that slide, the higher the current, the greater those electrons will be able to flow. Also, the lower the resistance, the higher the current, because the electrons will be able to flow easier. Now, this is summarized in an equation as I equals V divided by R, but I found that my students tend to struggle working with that equation, even though it's just like speed equals distance over time. So I will give you the equation as V equals IR. I just rearranged it for you, so it's a little bit simpler for you to manipulate when you need to rework it. So V equals IR, just a rearranged version of Ohm's law. So V is voltage difference, and it's measured in volts. I is your current, and it is measured in amperes or amps. And then remember, R is your resistance, and it is measured in ohms. So again, just to reiterate, current, or the flow of electrons, depends on these two things, on voltage difference and resistance. The greater the voltage difference, the greater the flow, because there's going to be this stronger push, this steeper slide to move more electrons through. Also, the lower the resistance, the greater the flow, because resistance causes some of the energy that could be converted to electrical energy to be converted to thermal energy. There's going to be more friction there, and so that's obviously going to affect our current. So let's do an example of this math, and then we'll practice it. What is the voltage difference that flows through a copper wire if a current of 0.75 amps is flowing through it? The resistance of the wire is 10 ohms. All right, what are we looking for? We're looking for voltage difference. What do we know? Current is 0.75 amps and resistance is 10 ohms. Our equation is V equals IR. We're looking for voltage and V is already isolated, so we don't need to rearrange here. We can just go ahead and plug in. So V equals I, which is 0.75, times R, which is 10. 0.75 times 10 is 7.5, and my units for voltage difference is volts. All right, now I would like you to pause the slide and work through these three problems. These are They couldn't get any harder than this. These are the three that you would see for this content. And then when you're ready, press play and you can see the answers. And now we're going to move on and practice more together in class.